It's my pleasure to be affiliated with Morton and Chemo Analytics and be a part of their toolkit with Design Expert. And today I want to talk to you a little bit about what Design Expert can do to make design of experiments easy and yet more powerful than any other tool that you might be able to get on the marketplace. As Morton mentioned, we will keep the audio muted. However, please feel free to jot down questions and then later address them to mark@staties.com, and I'd be happy to accommodate. Here's a picture of me on the bottom left, and just to practice our facility with the controls on the GoToWebinar and to give me some feedback that you're able to see me and hear me, press that raise hand button that you see on the control panel. So on the control panel, you should see a hand and press that. Okay, Rich, Patrick, I'm just naming out a few names here, Michael, Martin. Okay, that's enough. It gives me a good sampling. I feel that from the sampling of people that have raised their hands, I am probably getting through with the audio and the video, so thank you for that. I'm going to set the hands back down, and from time to time, I'll ask you to raise your hands just to make sure that I'm getting through okay, and to get some feedback. So the main thing here is that we have a series of books that are available, and these books will help you fill in a lot of gaps because I only have about half an hour to talk today. What I highly recommend would be, if you are not real familiar with the design of experiments tools, you start with this first one, DOE Simplified, and that'll cover the fractional and full factorials, the main core of DOE that does the screening and characterization. Now, if you're going to move on to optimizing any kind of a process, and this could be manufacturing process, it could be an analytical column that you're trying to optimize, whatever it might be that has numeric factors, the tool of response surface methods, or RSM, is very useful as a follow-up to screening and characterization that you get from the factorial designs that are covered in DOE Simplified. So the second book then that is a companion to the first is the RSM Simplified. Then there's something completely different over here on the right, and this would be for people that are doing formulation. And certainly anybody in process industries, food, pharmaceutical, chemical, plastics, there's any, you name it, any number of industries that have chemists, and these chemists need to consider using mixture design for optimal formulation, and this is covered in the third book. So these books are readily available, they're fairly economical, they can be purchased in the form of ebooks via Amazon, so it's good to study these tools before you put them to good use. So what's in it for me, or with them for this webinar, is really that I'm going to demonstrate or demo a number of features across a broad array of tools for design of experiments. And because the time is short, my expectations are not real high, but I would like to see that you gain an appreciation for multi-factor testing and see that the use of planned experimentation and tools that I present provide a tried and true strategy of experimentation, and that you will be inspired to use these tools. Many of you have them already in your hands, with the bundle that is provided by Chemo with their Unscrambler software. And others have bought and they're just using Design Expert and maybe not using those as much as they could. So hopefully you'll be inspired and you will inspire others. Now, I always like to start with what I call the elevator speech, when you have to get on for just a few minutes with somebody and convince them that a tool should be used, by talking about multi-factor testing strategy, as opposed to one factor at a time, which is a traditional scientific method. And for this, a good story is developed by George Box in a quality engineering column years ago, and it tells about his experience with Christer Hellstrand with SKF in Sweden, who was threatened by Japanese that came in with a new bearing that was going to take away their market. And so he needed to study this, but they had failed so far to come up with the answer. And here are the data that they had collected. And this is the bearing life in hours in an accelerated test. And it turned out that their current operating level for the life was not sufficient. They needed to double that level. So they tried testing 3 factors, A, B, and C. Now, A is actually a heat treatment. And when they increased the heat treatment from a low level minus to a high level plus, they got an increase in the life, but it didn't double the amount of life, so it was a failure. They then turned their attention to factor B, which, as it turns out, is something called osculation. And osculation is the kiss of the bearing to the cage. And they went from a lower kiss or osculation to a higher kiss. And it did increase the life, but not enough. And then finally, and this was the most radical change, they tried using a plastic raceway in the bearing versus a metal raceway. And this was going to be a cost savings, and they didn't really expect it to help. Surprisingly, it didn't hurt, but it didn't help enough either to make the results that they wanted. Now you're looking at this and you're saying, Mark, why don't we go up here? Because obviously here's the answer. Well, the engineers were mired in this one factor at a time, or traditional scientific method, and they were stuck in the corner here. But all the whole time, it turned out, as soon as George Box worked with Krister to develop what's called a 2-level design, which is represented with the number 2, with 3 factors that do all 8 combinations, or 2 to the 3. They then saw that there was an interaction that was synergistic, and this happens to be the AB interaction, or the interaction of the heat with the oscillation. That's the key, and that made the breakthrough. All this seems fairly obvious, but surprisingly, many people just never think that you can vary all of the factors simultaneously, and you do this in a parallel approach, which of course is always more effective and more efficient than a serial approach. Now, what a lot of people don't realize is not only does the combination of things end up being the key, but also that it's more efficient because of this parallel processing. And what we have with this factorial design is we have 4 at the high level of each factor, for example, A at the high level, and 4 at the low level of each factor, such as A at the low level. So you have 4 by 4 comparisons, and these comparisons also work from the bottom to the top for B and from the front to the back for C. So the OFAT experimenter could match that by doing 4 at the baseline and then 4 at each of the high levels. But if they did that, they'd end up with 16 runs, which is twice as many as the 2-level design. As the number of factors goes up, the 2-level design becomes more and more efficient. So here we have a way to do something more effective to find these combinations of things and more efficient. So it makes no sense to continue with OFAT. So let's talk about 2-level design in a little more depth. The 2-level design that was developed by Sir Ronald Fisher in the 20s and 30s is very, very effective, as I've mentioned, and efficient. But if you use it in a smart way, in an iterative fashion, by first doing a medium resolution design, which we color code yellow, that just is used to screen main effects and try to screen down to fewer factors that are the vital factors. And then in the second phase, you then run a higher resolution design, could be a full factorial, and try to resolve the 2-factor interactions like the one I showed you for the bearings. So this 2-phase approach, which is screening and characterization, is highly recommended to try to quickly get to a much better process condition. So let's look at an example. This dates from my own experience with a company in Chicago called Sara Lee. And while I was teaching a bunch of food scientists how to do 2-level design, coincidentally, they were approached by their biggest client, and they were confronted with a quality problem, which was unsightly pitting on the bottom of the crust. This was something they hadn't ever thought about before, but a competitor of Sara Lee was complaining, and they potentially were going to lose this large client. So literally during the class, I worked with the food scientists. They ran out of the class, and they did what I call a troubleshooting study on 6 factors that they felt might affect this pitting: the dough temperature, amount of shortening temperature, rework, aging, and conditioner. Now they only could do at the most 24 runs. And if you do the math on a 2-level design up to the 6th power, I think it comes out to 64 runs, which is too many. But no problem, you can do what's called a fractional design, and I'll show you the array of fractional design choices. So here we see our color-coded design builder and design expert. This is a slightly older version, but it's simpler. And we can see that for 6 factors, we could do all possible combinations, but that would be too many at 64. We can go one step back and do what's called a half fraction at 32, and that would be good because it would be high resolution. It would even tell you about two-factor interactions. However, it's still too many. So then they said, well, I guess the best we can do is 16 runs using this classical standard design builder. Unfortunately, that crosses a line and becomes a lower resolution, what we call a medium resolution. It's normally used for screening of main effects only, but they really thought there would be some interactions, so they weren't happy with that. But no worries, Design Expert comes to the rescue with modern DOE options that were developed within the 2000s. And these are called modern minimum run or MR designs. And we can work with up to 50 factors, which is plenty. These provide considerable savings over the standard fractions. So in the case of the Sara Lee pies, they had 6 factors. They could only afford 24 runs, and yet they felt there was going to be interactions. So they wanted to do this characterization for the two-factor interactions. So then this minimum run 5, which is the resolution number that gives you the two-factor interactions, came to the rescue. And we also have MR designs for screening, which are used just for main effects. And of course, those will have fewer number of runs. But in this case, they wanted to do a characterization. By the way, I have a reference on there, and after we finish this series of webinars, Morton will post a PDF of these slides. There also will be a recording. So now using Design Expert, let's rebuild this design so you can see how it's done. And they actually had 2 other things they wanted to work on besides the pitting, which was most important. Also, the raw spot and bake shrink needed to be managed, and they couldn't be above anything more than 15 and 1.5 respectively. So let's see if we can pull up Design Expert. I'm going to escape out of this slide and pull up Design Expert. All right, now I need to ask if you see a splash screen that says Design Expert version 12. If you do, will you press that raise hand button? If you see the Design Expert splash screen, there you go. Okay, Andrea, Albert, going from the top and back down to the bottom. Stephen, okay, so that's great. We've got sufficient sample size here that tells me that we're getting through. So now what I'm going to do is open up this pies file, and I will control mouse wheel to make the display a little bit smaller so you can see the whole thing at once. And you'll see that we have here all the results collected for various conditions of the different factors. Now, how did we get to this point? I'll rebuild this. So I'm going to rebuild this using the current factors and responses, and we'll be able to see that if we went to the regular 2-level design, it would start off with all the possible combinations, which is way too many at 64. Then as we try to cut back, the best we can do is this yellow design, which is a screening type of design that only gives you main effects. But now if we go to this minimum run characterize for the 6 factors, here you see the option of 22 runs. So this is the minimum number of runs, sometimes +1 to balance out the pluses and minuses, that were invented by statisticians. And what we do next is fairly straightforward. We're just going to, I'm going to switch this to horizontal view, enter in the names of the factors, the units of measure. We can put in numeric or categoric factors if they're 2 levels. These are all numeric. Then the low and the high levels are entered in. Next, we see an alias structure, which tells us that all main effects are clear of anything less than 3 factors, and all 2-factor interactions are also clear. It's complicated, but suffice it to say that this will characterize main effects and 2-factor interactions. Now we have, the next step is entering in however many responses we have. We have 3. The names are listed here, and then we have the units, but what's really important at this stage is we have an inline power calculator. So once the food scientists identified what was a minimum difference that would be important to them as what we call the signal, quote unquote, and then identified what the normal variation is as they produce these pies in the pitting. This created a signal to noise ratio that then enters into a power calculation, and you can see the power calculations here, and it turns out that it's plenty high. We say as a rule of thumb, if it's 80% or more, that's sufficient. If this power was not sufficient, you would have to go back to a bigger design and then have to see that we're clear to doing more than 24 or 22 runs. But it is okay, so that's fine. We finish. Now I'm going to collect the data back up again and control mouse wheel it down again so we can see. So the first thing I always suggest is just look at the data. And according to our specifications, we needed to get less than 20 on the pits. So if I sort this from low to high, we see that there's some results that have way more pits than what we need, but there's lots of results that are less. So this is promising. It shows a good spread and that we have a chance to accomplish our mission. Keeping in mind also we have to worry about raw spots and bake shrink. So the first thing I would do is I would use the tools in Design Expert to graph and just to get simple scatter plots. And we have this color-coded correlation grid here. And what you can do then is you can see by the colors if there's positive correlation like there is with dough temperature on the bake shrink, or positive correlation even higher on the pitting. And then the bluer colors are negative correlations, like the amount of shortening is negative, although it's a good thing. We want that pitting to be less. And then when you see a white square there, that means there's really not any correlation. Okay, and then if we look at the pitting versus the pitting, of course, that's a total 100% correlation positive, so that's the dark red. And then the factors themselves in a standard design would show no correlation, but because this is a minimum run design, it gets a little bit more complicated. So without further belaboring of the graphs, let's just go right to the analysis. Now, it turns out that this pitting response, because of the wide range that we have, 63-fold, it says at the bottom here. Using no transformation doesn't work so well as using a log transformation. This is like using log paper sometimes for things that have a wide range. And I'll show you a diagnostic that supports that. So in the base 10 scale, we then calculate the effects going from low to high. And we plot those on a special type of paper called half normal paper, where the y-axis is scaled so that the trivial many effects near zero fall on a straight line, and over here to the right are the effects that are standing out. Now, these effects, I'm going to clear the selection. You can select, one at a time, starting with the biggest effect, which is the dough temperature. The next biggest effect is the interaction of dough temperature with the amount of shortening. Aging of the dough is an effect, and then I've got the interaction of B, which is the amount of shortening, with E, which is the aging. And we have a pretty good family of effects here, but one thing we're missing is the main effect of B. And the software will identify that this would form a ill-formulated polynomial model, and it tells you you have to maintain hierarchy if you don't want to get off on your predictions. So then if you say yes to it, it adds the shortening back in again. So B is there to support the BE interaction. Now, if I was presenting this to management, I would go to a different representation called a Pareto chart. I really like this because it's really easy to digest that the dough temperature stands way above everything. We've got the interaction AB, the aging E, BE, and then notice that the amount of shortening does go up above the t-value limit, but it doesn't go above this red line, which is a better way of calculating the significance by doing a correction for the multiple pairwise testing called a Bonferroni test. So anything above the red line is definitely significant, below the black line is not, and then there's this in-between area, and B falls into that, but it has to be part of the model because of it being part of the BE interaction. Now, in the analysis of variance, we see these multi-views. Above, I've got this control panel. I'm just going to go to the single view of it here, and then do the control mouse wheel to increase the size. And of course, we want to look at these p-values and remember that p is in there to support the model. And so don't be worried that it's not quite as significant. Now in the diagnostics, there's some things we can look at. I can't go through all the things that are here, but one thing I want to point out is that this diagnostic called Box-Cox is where we see that it does recommend that log will give us fewer residuals from our model. In other words, it'll fit stronger. So that's the reason we do that. Another one I like to look at is just the normal plot to make sure nothing's out of line. They all fit this special paper, which is a full normal paper. So that tells me that we've got a good fit. And then another one I like is the residuals versus run. And this is like a control chart with the limits in red. And we don't see any particular trends or anything out of line. So with this in hand, now I'm ready to look at the model graphs. And we see some interesting things happening straight away with this A-B interaction, that we get a very high level of pitting if we let the dough temperature go up at the same time that we reduce the amount of shortening, and we get a really bad result that's above specification. So looking at this, we realize that as long as we avoid that condition, and for example, if we go to the high level of shortening, then we get this flat red line, and that would be a robust operating condition. So that was an answer for the food scientists. Then over here on the right here, we have other possibilities. We've got also the BE interaction. Now, if we go ahead and move the amount of shortening down, the amount of shortening is, we want the dough temperature. Well, that shouldn't really, okay, look, we can see that if we move the dough temperature down, then we get all our results in terms of this interaction of amount of shortening and aging, falling below the pitting. So we have a very dynamic situation here because of the two-factor interactions, and they're linked. And so we get a very dynamic interaction. Now, a really simple approach to looking at this is actually to use something called a cube plot, which I showed you with the bearing case. This gives us all three factors, the A, B, and E, and I think I'll put A as the X1 axis, and then B as the X2 axis, and E as the X3 axis. Okay, so now we have A, dough temperature, as A. Amount of shortening is going from bottom to top and aging from front to back. And on this, we can look at the amount of pits, and we can see a really bad combination at the lower bottom right, which is that high dough temperature with low amount of shortening. But there's many other possibilities that will get the number of pits reduced. Now we go through a similar analysis with the raw spot using the half normal plot. On the left, we can see that we picked out two main effects, and on the right, we can see how they stand out on the Pareto chart. These are significant for p-values. They diagnose well, and you can see the multi-view is helping us here. And then here you just have two main effects, and you can, decide that you want to go high dough temperature as far as the raw spots are concerned, and you want to go low amount of shortening. Now we may get into some conflicts between these different responses, so we'll look at that in just a minute. And finally, the bake shrink. Again, we use the half normal plot to select. So normally it would start off like this, and you would be picking these from right to left until no more stand off the line. The rest are trivial many at the left. Then on the right, you're verifying, and you can see that the ones you picked do indeed stand above the red line, and the others are below the black line. So that's a clean separation. And the p-values are good. And diagnostics are good. And here it's just, a couple of main effects again. Three of them, I guess we could look on the cube plot and draw some conclusion from that. So after we finish, analyzing each individual response and feeling we've got good models, the beauty of Design Expert is you can then go to a multiple response optimization, and we go in here and we say we've got to have less than 20 pits. We have to have raw spots less than 15. And the bake shrink, which actually analyzed in the square root scale according to the Box-Cox transform, we want to get less than 1.5. Then the program, finds the most desirable solution by doing a search throughout the region, and it says, if you get the dough temperature down, amount of shortening down, the shortening temperature doesn't matter, you can keep in the middle on those, same thing for rework. And then the aging up and the conditioner up, we then can get pitting to a minimum with sufficiently low raw spot and bake shrink, barely. This was a solution, and that solved the problem, and I was able to finish my class with the Sara Lee food scientists, and they were very happy to make immediate use of these tools of two-level design. It was quite a big success. So that's my first presentation, which is the core factorial design. All right, next I'm going to move on to the next phase of strategy of experimentation. So this strategy of experimentation allows us to first screen unknown factors and screen them down to just a vital few first using one of these yellow designs, or what we call a minimum run resolution 4. And these are designs that will help us with main effects. So I use the initial ME for main effects. So we're screening on main effects first before we do an in-depth characterization. And we take these known factors and we hold them off to the side temporarily, merge together at this point. And then the next phase is the characterization. And these are the green designs. They could be a full factorial, which are the white squares, or the MR5 characterization designs. Now, what I didn't mention is typically at this point you add what are called center points. These center points are in the middle of the space, and they allow us, if you do multiples of them, to test for something called curvature. And that means that the two-factor interaction model, which does give you some twistiness to the shape of the space, but it doesn't give you the pure curvature, you're going to come up short without doing further work. And so if it is curved, you're going to have to go to the next phase and use a response surface method. Either start over with one or augment the existing design. So that's what I want to talk about next. And what you can produce with RSM are these beautiful graphics like we see here with this rising ridge. Now notice that there's some green points cutting across here. And you may look at that and say, now, I wonder why anybody would do that if you can clearly see that the yield of this pure vitamin E that we worked on could be increased much higher than if we stayed at this point. But believe it or not, OFAT, one factor at a time approach, failed in this case. This was an experience I had with a PhD chemist named Bill. He knew the OFAT very well because that was scientific method, and he was very methodical in changing the factor A levels across many points here and drawing out this beautiful curve and then seeing where the maximum was on A. Then he carefully fixed A and he went to factor B and did the same thing, and he got this beautiful curve. And in the end, he said, this is where we're going to get the maximum yield, which he said might be about 77%. So I said, fine, Bill, and I took the recipe he gave me, which is here at the middle, and I said, I'm going to do a series of other runs above and beyond, and I did a very simple design. It's actually a 3-level design on 2 factors with 9 runs, and you can see it's just simply covering, more combinations here. And when I did that, I was able to fit a model that was more sophisticated in terms of predicting the response Y as a function of not just one factor and the other main effects, or even the interaction which you can do with the 2-level design, which is x of I, x of j, but also then by having this many levels, I can fit the squared terms, x of I squared and x of j squared. When I do this creates something called a quadratic model. Sorry for my scribblings. The quadratic model can fit all kinds of surfaces such as this rising ridge, and with this you can see that if we can get to these combinations here, we can get up to near 95%. So that was a good illustration of how OFAT falls off, and using, in this case, a multi-factor approach of response surface methods, we're able to get, a much better result, and it was worth millions of dollars. So let's look at a similar case study. This case study, again, is a chemical process. We've got 3 factors: time, temperature, catalyst. We've got 2 responses: conversion. The second response is really targeted, and it's a quality response. So the first response, of course, is a yield response, and the second is a quality. So we have to get not only high yield, but it's got to be high quality. Now, for convenience, we wanted to break it into 2 blocks. So we did this in 1 block of a 2-level factorial, which is this cubicle space here. And we added center points, which are the red dots in the middle. Then a standard structure is called the central composite, invented by George Box in 1951. And Box picked up the mantle from Fisher. He married Joan Fisher, Ronald Fisher's daughter, and he studied under Ronald Fisher. But Fisher never got to this point that Box could see, where if we put these points here and put them outside of the box to get leverage, we then can fit a more sophisticated polynomial model. And these are going to be done in the second block of runs. So I'm going to show you that. And I'm going to go back to Design Expert. And I'm going to close out this design. And I'm going to open the RSM design. Now I need to ask you, if you're seeing this, what you should see on your screen is that we've got 2 groups or blocks of runs. One is in machine 1 and the other is in machine 2. So we have 2 reactors. Then you should see that there's the factors of time, temperature, catalyst, and then the 2 responses of conversion and activity. If you see that, raise your hand. Looks like some people are raising their hand already and seeing it. Good to see Sarab in there and a number of other people. Okay, great. So I'm going to put the hands down again. And now let me tell you about this RSM. What I'm going to do is rebuild this. And so now you can see that we've gone from a full array of options under factorial. We explored the design builder, which is developed by Fisher. We call it a classical or standard design builder. We talked about the minimum run designs that are more modern, that can cut down the number of runs for characterizing and screening. We didn't talk about the fact that we also have the ability to do factors that are hard to change, and this is called a split plot. And you can actually deal with things like temperature that can't be easily randomized. That's a cool feature that we have. I don't have time to discuss it. So we have lots of different options. We have multi-level categoric options where you can do any number of different factors and any number of levels. And even we have optimal custom designs that can reduce down the number of runs using a computer choice algorithm called D-optimal. And we also have custom for split plot. But at this point, we're not on the factorial, we're on the response surface. Now, what I'm suggesting to start with, if you can cover all the ranges, is you go with a central composite design, because there's a tried and true approach, and you can see the layout of it here. When I press the light bulb button, that gives you help immediately at your fingertips. And there's more information in our help when you press that light bulb button. And also we have a complete set of contents for help. There's a tremendous amount of help in the program and tutorials. So lots of help. All right. So now this design, we're just going to go with kind of the standard selections here. And so we simply add in the different factors that we have. And I think we've got, resetting this, we've got 3 numeric factors: time, temperature, catalyst, the units of measure, the ranges. Over here, it tells you that you're going to push out of these factorial levels low and high. We're doing it in 2 blocks, which is the option here. And then there's other options under the covers. I won't get into it, but lots of bells and whistles available once you understand better, what would be good and what would be bad to do. And doing this in 2 blocks is going to help us do side-by-side running, machine 1 with operator 1, machine 2 with operator 2. There is also, then after we put in the response measures, a tool for sizing the designs, but it's got to be something different than the power because these designs are non-orthogonal. So we have a process that you would study, it's detailed in the books, called fraction of design space sizing, or FDS sizing. So just maybe make a note of the term FDS and pursue that after the presentation. Now we have a recipe sheet. We give this to machine 1. We cut right here the sheet of paper in half. We give the second sheet of paper to the guy at machine 2. They run these side by side with the conditions shown in random order. You notice that the second machine has got those more extreme axial or star points, but there's also in the second block a series of runs that are the same as in the first block that are at the center of the space, or what we call the center point, that link together the two blocks. Now I'm going to collect the data, and I'm going to have to skip a lot of the details on this because of the time constraint, but we do know that we want to maximize conversion, so I probably would just sort this and see if we get some good conversions. We do. But on the other hand, we have to get activity between 60 to 66. And some of the results are outside of that range. So I'm just highlighting the ones that are between 60 to 66. Then I look and see if any of those are high yield. And I can see by inspection that we might have a chance of getting within the activity range and at high yield. If it was more important to get the activity near to 63, we'd have to give up some conversion. But before we get too far ahead of ourselves, you could look at the graph columns. However, we don't get as good of a view of things with the central composite because of the way it's laid out. We could look at some things like the block. How does a block affect the conversion? And let's go down here and look at the conversion versus block instead. Okay, this is a little bit better. So between machine 1 and machine 2, there's differences, but remember they have different combinations of runs. So if we colored this by the space point type and we focus on the red squares, then we can compare the center points in the first block to the center points in the second block. And maybe machine 2 has got a little higher conversion, but no worries because we blocked that out of the model. So that's not going to cause a bias to our results. And then we could look at the block effect on activity. It doesn't look like focusing on the red squares there's much of a difference there. So that just gives us kind of a pre-analysis of what's going on. But now we're going to go in and we're going to fit a series of models all the way up to the design for model, which is the quadratic. And if it turns out that there's no advantage to putting in main effects even, we would just use a mean. If there's no advantage above the main effects of the linear model to add two-factor interactions, we wouldn't do that. But as we move up the ladder here, we see that the additional terms are adding significantly to the fit all the way up to the quadratic. And the quadratic has less lack of fit, and it's got higher R-squared values. So the program has scored this and suggested that we would just stick with the design for model, which is quadratic. Now we go to the ANOVA and we look at p-values, and you may find that some of these terms are a little bit high on p-value. We certainly could take those out of the model, either manually or through an automated reduction capability that I don't have time to demonstrate. We'll just go with the entire model. It won't be much of a difference one way or the other if we include or exclude the insignificant terms. So going with the whole model, we look at the diagnostics. There's no recommended transformation, no other problems. And now we can generate these beautiful contour graphs and look for the hot spots for the conversion up here. You can set flags. And then why not look in 3D view? And we can slide this catalyst around and see if we can get a higher amount. And it looks like if I go to the high end of the catalyst, I can get a really good result up here. And that'll give us a very high yield. 97% I'm getting there. It's a very small number, but that's very high, near 100%. Now we have to be careful because we could get a very high conversion and produce a lot of bad product unless we can get the activity within range. To fit that one, it turns out that we don't get significant improvements by adding two-factor or the squared terms. So the program recognizes there's no reason to overfit the data, and it suggests we just stay with the linear model. And then we can look at the p-values on that. And actually, even the temperature is not significant. I'm not going to take that out. It doesn't really matter one way or the other, but you certainly could reduce this out of the model. And then the diagnostics are good. And finally, the model graphs are not as interesting because they're just straight lines on the contour and just a planar surface. What does catalyst do? Okay, we got to be careful because catalyst is affecting this activity. So now, is there a way to get a high yield with the activity within range? And the answer to that is yes, but we find this by going to the numeric optimizer, which finds a desirable combination of conversion. We can also change the relative importance of these. I won't do it. Let's say they're equally important, and activity's got to hit the target. And then the program searches out the solution, and we're going to find that there is a solution with kind of a mid-time, high temperature, mid-catalyst that gives us above 90 on the conversion and hits the activity straight away. So again, a success. Of course, you don't think I would show you something if it wasn't a success, right? That I wouldn't do, but of course, not all DOEs are going to be successful. But the thing I've found is you always learn from doing a planned experiment. Even if it means that the region you're in is surely not going to work, that's a win. Okay, last but not least in our toolkit is the mixture design. And now I've gone over the time a bit. So I just want to say that with this, we're going to focus on factors that really are ingredients or components of a mixture. Then we will fix the total. And when we do this, it avoids situations like this where we're making lemonade and we have two conditions in a two-level design that are basically the same, which are the 1-to-1 on the lower left and the 2-to-2 when it's just the taste of it that matters. So in cases like this, we need to condense down, and this would be a good way of looking at it using mixture design, whereas the lemons go down, the sugar water goes up. And in this case, we fit a special mixture model that is different than a normal polynomial, but it gives us an idea that there's some nonlinear blending here where you mix up lemons and water together tastes better than either one alone. So these mixture models and mixture designs are very effective for formulation. And in this case, we're going to use specialized graphs that are called ternary or triangular diagrams. So we don't use this space anymore, but this space here that has pure A, pure B, pure C, binary blends are on the edges, and then the complete blends are in the middle. And this paper you can set up where it's ruled from 0 to 100%. And for example, metallurgists would use this for stainless steel. And here we're going from 0 for the chromium to 100% from bottom to top, and from 0 on the iron to 100% from right to left. And then the last ingredient is nickel from 0 to 100%. And it turns out that if you set this up at 18% chromium and you set it up at 8% nickel, and then the difference of this is 18 plus 8 is equal to 26, so then the rest of it is 74% for the iron. And that's cutting across this way. So let me just ask though, how many of you have seen a triangular diagram like this? Raise your hand if you're familiar with that. Anybody? Raising their hand, seeing a triangular diagram? I don't see any here. Okay, so this might be something a little bit different for the bulk of people. So I'm not going to get into it then, but suffice it to say that there are tools available in Design Expert, and this comes actually from a tutorial that you can go through that explains how the detergent chemists were able to actually come up with a way to optimize. And just kind of cutting to the chase on this using Design Expert on the mix is that there are complete tools available under this mixture, including optimal custom, which is oftentimes used because the constraints don't form a simple triangle. And of course, you can set up a nice little recipe sheet. The chemists can, make the different ingredients. They can measure things like viscosity and the turbidity or the cloudiness. And once they take that data, they can fit it, and we can create these models. This is a view of the two models that have the main component effects, nonlinear blending, and even a 3-part nonlinear blending for the turbidity is fitted. And once that's done, then again, you can do your targets and your minimize, maximize. In this case, they want to hit a certain viscosity on the detergent, and they want to make sure it's not too turbid or cloudy. And here's the solution and how you can mix this up and accomplish your objectives. And there's even a way to overlay the parts that don't meet specification. And it turns out in this case, if you get in the middle here, it gets too cloudy. And if you get on the outside, it's not got the right viscosity. But there's certain windows which are outlined in yellow. And we happen to be located in this upper window at the top here with the most desirable combination. So that's that. We also have the ability of doing combinations of things, which are the shown here. For example, a paint chemist wanted to improve the hardness of the coating on the automobile and still get a high solids for environmental reason. And they wanted to look at 2 vendors, 3 different crosslinkers, and different combinations of the ingredients. And you could even change some process conditions. And using an optimal design, you can do all of the above. Just believe me on that. The Design Expert can do almost any combination of factors, particularly with the optimal custom. So it's incredibly versatile. So now I'm over, so I'm just going to conclude and say, my main take-home message is don't use a one factor at a time approach, but use a multi-factor. And there's the various tools that we have, the 2-level designs for screening characterization. We've got the optimization tools with RSM and mixture design. So with Design Expert, it makes the DOE easy and yet powerful. And whereas other packages are out there that can do all kinds of statistical things, it's like a Swiss Army knife using that when you really need a screwdriver. I think Camo has done a great job of putting our product together with theirs so that you get the full advantage of a dedicated MVA tool and a dedicated DOE tool. With that, I want to say much appreciation to Camo Analytics for hosting, and thank you all for listening.